When you hammer an iron nail, you apply force on the flat side of the nail. The pointed side of the nail, which is in contact with the wall, then applies the force on the wall and tries to pierce it. Now let me ask you an interesting question. What will happen if you hammer the pointed side and try to pierce the flat side of the nail? You will find it difficult to push the flat face of the nail through the wall even if you apply more force than you did in the first case. What is the reason for this? The reason is that the pressure applied by the tip of the nail on the wall is more than the pressure applied by the nail's flat surface. But the question is why? First, notice that the area of the tip of the nail is very less as compared to the area of its flat surface. This tells us that the area of the surface on which the force is applied matters. We will understand this in detail, but first let us define pressure. We define pressure as the perpendicular force acting on the surface of an object per unit area on which it's acting. It's easy. Force acting per unit area. We already know that the SI unit of force is Newton, denoted by N, and that of the area is meter squared. So the SI unit of pressure is Newton per meter squared. It is also called pascal, which is denoted by PA. Why is it called pascal? It is given this name to honor the achievements of a French scientist named Blaise Pascal for his contributions in hydrostatics and hydrodynamics. Observe the equation carefully. Area is in the denominator of the fraction. What is this area? Well, this area is nothing but the area on which force is applied. Say I keep the force constant and I keep increasing this area. What will happen to the pressure? Will the pressure increase or decrease? Use pure mathematical logic to answer this. If I have a fraction and I keep the term in the numerator constant and keep increasing the term in the denominator, then will the fraction increase or decrease? Surely it will decrease. So the pressure will decrease if I increase the area while keeping the force constant. With this newfound knowledge, let's go back to the example we saw earlier, the nail and the wall. Notice that we are also applying the force perpendicular to the surface of the wall. The angle between the nail and the wall is 90 degrees and not anything else. If you notice, the tip of the nail has a very small area compared to the flat surface of the nail, and hence the area of contact with the wall reduces to great extent in the first case. Hence, the pressure applied by the tip on the wall is greater than the pressure applied by the flat surface. That is why it is easy for the tip of the nail to penetrate through the wall. You can even use drill machines to drill the hole into the wall. You see that it has the pointed tip for the same reason. You can easily cut the vegetables using the cutting edge of the knife. But if you use the blunt edge of the knife, it will be difficult to penetrate it in. What is the reason in this case? Well, in the first sight, the two edges might look the same to us. But if you look at them carefully, the cutting edge has small triangle-like shapes with sharp outer points. The other edge has nothing of these. So if you cut a vegetable with a cutting edge, the area of contact between the vegetable and the knife is greatly reduced. Hence, more pressure is applied on the vegetables using cutting edge of the knife. Area used to cut the trees also have sharp cutting edges instead of placid ones. It increases the pressure on the tree due to the less area of contact. The examples that we've seen so far are applications of high pressure. It's about how high pressure is useful to us in some cases. But it is not always the case. There are situations where we require low pressure. Let us see some applications or advantages of low pressure. We use snowshoes to walk on snow. The reason for that is simple. Due to the larger area in contact with the snow, snowshoes reduces the pressure on the snow. We are able to walk on it without our feet sinking deep inside. In case of normal shoes, due to comparatively smaller area of contact, the pressure on snow is more and it sinks our feet deep inside. Note that the force applied on the snow in both the cases is the same. This force is nothing but our weight on the snow. Have you ever wondered why the wheels of an army tank run on the steel tracks rather on the ground? Notice that the wheels are on steel tracks and are not touching the ground. The army tank is huge in size. If the wheels run on ground, due to less contact area with the ground, the pressure on the ground will be massive. However, the tracks have much larger area of contact with the ground and hence the pressure on the ground is reduced to a great extent. In all the examples that we have seen in this video, it is the solid which is applying pressure on another solid. Do liquids also apply pressure? We will see that in the next video.